We now want to start talking about the behavior of fluids. Right, the behavior of fluids. And to do so, we need to first introduce the concept of something that doesn't quite seem like it's necessarily related to the generic behavior of fluids, but it will become readily apparent very soon, and that is the idea of pressure. Okay? So what is pressure and how do we define it? Well, we define pressure, capital P, as the force that is exerted over a specific area. Okay? So imagine that I have two sheets, and this is a top-down view of one sheet, right? And this would be the top-down view of a second sheet, so I'll label this sheet 1, and we'll label this sheet 2, and this will be from the side view, right? And imagine I place two boxes. On the sheets, right? And from the top it would look something like this. We have boxes, and let's say the box, each box is, I don't know, let's say 2 by 2 in dimension. So it'll be 2 units this way and 2 units this way, right? So 2 units that way and 2 units that way. And we don't really care what the units are, but let's imagine that this box is, let's say it's 30 kilograms, and this box is only 2 kilograms. Well, we can easily deduce without too much thought which one will be exerting the greater pressure on the piece of paper. Obviously, the heavier one is going to be exerting the greater pressure on the paper, but exactly by how much is that pressure going to be greater than the second situation? Okay, so using this formula, pressure equals force per unit area, or force over area. What force is this 30 kilogram box going to be exerting on this piece of paper? Well, it's going to be exerting its weight downward, as this box will also be exerting its weight downward. And remember that weight is equal to mass times gravity. And so we can determine what the pressure is in both situations. And let's give these units. Let's give this 2 by 2 square, 2 by 2 square centimeters. Okay. And now what we can do is plug both of these situations into the formula for pressure. And we'll say that the pressure in situation 1 is equal to the force in situation 1 over the area, which the force in situation 1 was the weight for situation 1, which was the mass of box 1 times g, over, well, 2 by 2 would be 4, over 4 square centimeters. So this is going to be 30 times 10, and this is kilograms, and this is meters per second squared, over 4 square centimeters, or 4 times 10 to the negative 4 meters squared. The reason is 4 centimeters is equal to 4 times 10 to the negative 2 meters. So 4 square centimeters would then, I would have to take this factor, or let's write that 4 again. I would have to take this factor, I need to take this factor squared. Okay, so that gives me the 4 times 10 to the negative 4. All right, so that's where those units come from. So I didn't want you to be confused about that. But now that we've got that, we can do away. All right, and what does this come out to be? Well, 30 times 10 is going to be 300. This is going to be 300 newtons divided by 4 times 10 to the negative 4 square meters. The result is 750,000, and we now have a new unit, newtons over square meters. And we have a new name. We call those Pascals. Right, so the Newton per square meter is now known as the Pascal. And we write it as PA, so we don't just write a P and then get confused with the variable pressure. All right, so let's calculate the second pressure. So P2 is going to be F2 over A, or the second weight, and let's remind ourselves the mass was only 2 kilograms. And we had 4 times 10 to the negative 4 meters squared. Oh, whoops. That's the area, not gravity. So now we have 20 divided by 4 times 10 to the negative 4. Which is only 50,000. Pascals. Now, word of warning, okay, word of caution. Okay, these are extremely high pressures. Extremely high pressures, and the reason being, okay, it's really hard to cram 30 kilograms down into an object that's only 2 by 2 centimeters. Okay, that's really unrealistic in a sense. But just for example on how to actually calculate the pressure, the example holds. Okay, so how does this relate to fluids? Well, let's just imagine that I have a cup of water, and the water is, oh, I don't know, it has some depth D, right? Let's just let the water have some depth D. Now, if anybody's ever gone scuba diving, you know that the water pressure increases as you go downward, and that's because there's more weight on top of you. The water has more mass that's on top of you. So at the top, there's a little pressure pushing upward, and the reason being is that fluids exert pressure in all directions. So there's actually pressure being exerted in all directions, but as you go down, it gets larger. And when you're at the bottom, the pressure is extremely high, or I should say much higher than it is at the top. All right? So we can actually use this fact, the fact that there's pressure exerted in all directions in a fluid, we can use this fact to our benefit. And to actually make some sort of engineering ability out of this fact, we use what's called Pascal's principle. which states this. It states that any change in the pressure of an enclosed fluid is transmitted uniformly throughout the entire fluid. And how does that help us, right? Well, imagine now, not that I just have a glass of water, but imagine that I have a cylinder and there's some oil in it, or some sort of fluid, it doesn't really matter, and it's enclosed on three sides by the cylinder and on the top by a piston. Okay, and that piston I can push up and move down. And again, there's going to be small pressures at the top and large pressures at the bottom. But what happens if I push the piston down? Right? What happens if I push the piston down? What Pascal's principle is saying is that everywhere in the fluid, okay, the change in pressure is going to be uniform. So even though I have higher pressures down here and I have lower pressures down here, the change in pressure as I push down on the piston, the change in pressure will be uniform. So however much pressure is changed up here will be the same change in pressure that I experience down here. So everywhere experiences this exact same change in pressure. So, and of course there's also pressure exerted outward on the sides, and those get uniform changes. So those increase in length uniformly. Okay, so the change in pressure is the same everywhere. Now, how does this enable us to do something useful? Well, now imagine that I have a situation that looks like this. And in fact, let's actually make this side a little bit smaller. Okay, and these sides here have pistons on them that I can move up and down, and everywhere in here is a fluid right? Now we'll call this piston 1 and we'll call this piston 2, and what happens if I push down on this piston over here? Well, remember that there's pressure acting upward, and that pressure is going to be equal to the force times the area of the piston. Okay? So whatever force is pushing upward, the pressure will be that force times the area of the piston. Now I can rearrange this and say, well, the force 1 is going to equal the pressure at the first piston times the area there, and likewise, well, let's look at the situation before I push this down, right? All of this analysis still holds, but over here we also have pressure pushing up, but it's over a larger area. So when I rewrite the force on my second piston, if these are at the same level, then they'll experience the same equilibrium pressures, so I can get rid of my P subscripts. and I have this. But so if the pressures are the same, but area 2 is much larger than area 1, then I'm going to have the situation where F2 is larger than F1. Okay? Now, when I push down on piston 1, when I push down, this piston will move down some height, some distance. Let's move it down to here. And that will cause an increase in pressure everywhere. And because there's an increase in pressure everywhere, however much the pressure is increased over here will cause an increase in pressure over here. And now my system is no longer in equilibrium, so this increase in pressure increases this force, and that causes the second piston to move upward. So I can raise something very heavy. If I were to say maybe put a car on this side, I'm able to exert a very large force, a force that is equal to the change in pressure now, that P represents the change in pressure, times the area of the cylinder. In most cases, a cylinder is going to be circular, so it's going to be pi r squared, where r is the radius of the cylinder, or the radius of the cross-sectional circle anyway. And so this change in pressure here is going to exert a very large force upward, so I can lift things like cars or trucks or boulders or stuff of that nature. So this is the working principle behind the hydraulic jack. Okay, that's the working principle behind the hydraulic jack. And just to kind of give you a sense of how this works, let's do a quick example. So let's say that we have a force of 10 newtons applied to a circular piston with an area of 2 centimeters, 2 square centimeters, and the output piston has an area, this is A1, the output piston has an area of 100 square centimeters. So it's very much kind of like the system where we've just drawn, where this piston would have 2 square centimeters for its area, and over here the area would be 100 square centimeters. And I'm pushing down on my small piston with a force of 10 newtons, and I want to know with what force my second piston will be lifted. Right? I want to know with what force my second piston will be lifted. Well, if we go back here, remember that these pressures, because we're talking about the change in pressure, but the change in pressure is the same everywhere, the change in pressure here is going to be equal in each case. So I can say that the change in pressure due to force 1 over area 1 is going to be the same as the increase, or is going to be the same change in pressure that is causing the upward force on my second piston times my second piston's area. So if this P and this P are equal, then I can just set these equal to each other. So I have F1 over A1 equals F2 over A2, and I'm now have an equality, a ratio equality in fact, and I can solve this for F2 very simply by multiplying by A2 on both sides, and I get F2 is equal to F1 over A1 times A2, and sometimes this is written more compactly as F1 over the ratio F2 over A1. So my output force is simply going to be whatever my input force is times the ratio of the areas, right? So however larger my second area is to my initial area, if I just multiply that factor by my initial force, and that'll be my output force. So in this case, we're going to have F1 was 10 newtons, and A2 was 100 square centimeters, and A1 was 2 square centimeters. And we see that the final result is 50 newtons, which is in fact a factor of 50 times larger than 10 newtons. So this is a brief introduction to the hydraulic jack. Next time we will look at Galileo, or not Galileo, but Archimedes' principle, and then we will get into rates of flow of fluids. All right, we will see you all later.